Good morning. In this lecture, we'll be going through and demonstrating the recurrent neural networks, in short called as RNN, and its architectural variants, which will help us in time series forecasting. We implement the various architectural variants of RNN, such as vanilla RNN, also called as simple RNN, deep or stacked RNN, bidirectional RNN, and stateful RNN. The traditional neural networks that we come across in our daily life, they do not work well on the sequential data. That means whenever we need to do some time series forecasting, wherein the data samples depend on time or there are temporal dependencies between the data, then the traditional neural network do not have the internal memory. That is why it will not be able to capture the temporal dependency. But in case of recurrent neural network, it possesses an internal memory and therefore it can capture the temporal dependencies between the data. They do not assume the data to be independent of each other. So that's why today's implementation is all about RNN and its architectural variants on a Apple stock market data. So let us go through this collab file. So recurrent neural network, we are going to see the implementation of vanilla RNN, deep or stacked RNN, bidirectional RNN, and stateful RNN. So starting with the initial installation and importing the necessary libraries. So we need to install Y Finance because this Apple stock market data is available in the Yahoo Finance website. Therefore, we are installing this Y Finance. So as you can see in the code cell, this is pip install Y Finance. Once this installation is completed, we can import this particular Y Finance in the form of a short form, say YF. So that could be seen in the next code cell. So already the requirement is already satisfied because the installation is already completed in this code cell. So once this installation is completed, we are importing the necessary libraries. So the libraries required in this particular RNN programs are Y Finance as YF, then importing the NumPy as NP. This NumPy is required in order to deal with arrays, or whenever we need something called as numerical Python, we call this NumPy. And importing pandas as PD because pandas will help us in data handling, or whenever we have to read some CSV file, we make use of this pandas library. Whenever we need some kind of 2D plotting, we may make use of matplotlib.pyplot. This is a graphical library which will help us in getting different kinds of plots. Then from sklearn.preprocessing, we import a normalization technique called as min-max scalar. So sklearn is a library in which there is a submodule called as preprocessing, because scaling, normalization, all these are a part of pre-processing the data. Even before we give the data to model building, we pre-process the data. So in our implementation, or in case of the sequential data, we make use of min-max scalar. Apart from min-max scalar, there are other types of scaling like the z-score normalization, which could be used if the data is normally distributed. Sometimes we can also use decimal scaling normalization. So in case of min-max scalar, the data, the normalized data will lie in the range 0 to 1. So we will discuss like why it has to lie between 0 and 1 when we come to the pre-processing part. Then we have from TensorFlow, we have the Keras components, like we import sequential, we import the dense layer, simple RNN, bidirectional RNN, input layer, and so on. So the sequential layer or sequential function is required in order to linearly stack all the layers, like the input layers, the hidden layers, and the output layers. These has to be sequentially arranged. That's why we need this sequential function. Then we need this dense layer, which is a fully connected output layer. This is the one and only output layer, which is the fully connected layer. So therefore we call this dense function. And then we have the simple RNN function, because we already told that one of the architectural variants is simple RNN. So in order to call out that particular function, we need this simple RNN function. Then we also deal with bidirectional RNN, which will forward as well as backward process the data. That's why we need this bidirectional RNN. And then for defining the input layers, we need this input function. Followed by Keras component. We also import this Adam optimizer. Optimizer is required in order to update the model parameters in such a way that the loss is very minimal. So frequent updation of weights takes place, frequent updation of parameters takes place. So all those are in the control of this optimizer. So in this program, we are making use of the Adam optimizer. But apart from Adam optimizer, there are other optimizers like RMS prop, ADA grad, ADA delta. So based on the necessity, based on the applications, we can make use of certain optimizers. So this code cell tells all about importing the necessary libraries. Now coming to loading the stock market data set. So as mentioned earlier, the Apple stock market data is available in the Y Finance website. So from Y Finance, which is in short called as YF, we are trying to download the AAPL dataset, which is the Apple stock market dataset. And let us take this data for a period of 5 years. Let us take only 5 years data. And this auto adjust is equal to true. That is that particular argument is helping us in adjusting the splits or the dividends present in the data. And in the data set, we are making use of a feature called as closing price. So closing price is our target variable, which is the only feature which we are considering, and that is the most important feature whenever we deal with the stock market data. So this particular download downloading of the data set, we store in a variable called as df. So now let us display the first 10 rows of this particular data set. So df.head, head is a function which will help us in displaying the first few rows of the data set. So here we are explicitly mentioning it as 10. So we are able to see the 10 different first rows of the data set. So we can see the timestamp, nothing but the various dates and their years, corresponding year, and the closing price, which is given in terms of US dollars. So we could see $118.54, $124.48, $124.41 US dollars, and so on. So when we explore this data, when we come across all the rows in the data set, this might be in the range of hundreds or thousands or 10,000s. So here we can see hundreds, the values varying in terms of hundreds, but sometimes it could be thousands or 10,000 and many more. Now, once we have downloaded the data set and we have seen what are the contents present in the data set, let us see what is the shape of the data set, like how many rows and how many columns are present in the data set. Therefore, we make use of the shape function. We apply this shape function on the data set, that is df variable. We are able to see 1256 rows and 1 column. So there are 1256 different samples in the data set and 1 column, that is the closing price column or the feature. So once we have understood the various parameters or various features present in our data set, now coming to pre-processing the data. So as mentioned earlier, while importing the necessary libraries, it's already mentioned that we are making use of the min-max scaling. So the scaling or normalization is required whenever we have data in different ranges. So as seen here, we can see the 10 different rows of the data set varying in terms of hundreds. So always this neural networks or machine learning models have a tendency of aligning themselves towards the larger numerical values. So as the values become larger, they pose some bias towards those numerical values or the higher values. So in order to come across or in order to overcome those bias, we have to bring down those larger values into a proper scale or into a range. Maybe the range could be -1 to 1, or it could be sometimes like 0 to 1. So here we make use of the min-max scalar normalization, which will bring down the values from hundreds or thousands to 0 to 1. So we could see how this scaling works or min-max scaling works. So the scaled data or the new data what we get, we can call it as x scaled. It can be mathematically expressed as x minus x minimum divided by x max minus x minimum. So this is how we mathematically represent the min-max scaling. So here x is the original data. For this x, for every value of x, we will be able to get a new or the scaled data, that is the normalized data. So what we need to do is whatever closed price we have, the closed price, what happens in the scaling is all the values are arranged in the ascending order. Values are arranged in the ascending order, so that we will be able to get the minimum value and then the maximum value. So once the values are arranged, we start from the minimum value. So minimum value, suppose I am trying to get the scaled data for the minimum value, then this would be x minimum minus x minimum divided by x max minus x minimum. So in this case, what happens is the numerator turns to be 0. So 0 by anything is 0. So the minimum value or the minimum range for the scale data is 0. So likewise, we can get for any value present in a data set or present in the target variable. So now let us focus on the maximum value. So this happens to be the minimum value and this happens to be the maximum value. So let me now try to get the scaled data for this maximum value. So in that case, x scaled would be, now my original data in place of x, I would be representing the maximum value minus x minimum divided by x max minus x minimum. So in this case, the ratio would become 1. So min max scalar, the range, the new range would be 0 to 1. So after performing the scaling, the new values would lie in the range 0 and 1. So this will help in the neural network for easy convergence. The learning also would be easier because the values are in a particular range. So this is what we do under pre-processing. So we call this min-max a scalar in some variable called as scalar. We fit the scalar on the data frame or on the data set that we are using, that is df. We transform that data set into a scaled data. So we are storing it in a new variable called as scaled data. So once this is converted into array, we can see the various values of the closing price, which were earlier in terms of hundreds, is now converted into in the range 0 to 1. So we will be able to see values like 0.029, 0.063 up to 0.954. So values are in the range 0 to 1. So once the pre-processing of the data is done, now coming to defining the train test split, or defining what is our training data and what comes in the test data. So as I mentioned earlier, this is an example of a sequential data wherein the current value depends on the past values. Therefore, we call it as a time series data wherein it depends on time, or the current values depend on the previous values. So creation of data set is very important, or creation of a sequence from the data set is very important in this case. So we make use of a function, or we define a new function called as create a sequence. So this create sequence has to work on my data, which nothing but the data frame, on by setting some window size, or by setting the width of the sliding window. So here basically what we do is, suppose I take n number of samples. Those n number of samples could be considered as a particular sequence. So in my example, what I'm trying to do is 30 samples would comprise one sequence. So if I define that sequence as x of 0, I define that sequence as 0th sequence, then it would comprise the data from 0th sample to the 29 samples, which will help me in predicting the 30th sample. So 0 to 29 is altogether 30 samples, which is giving me one sequence, and then with the help of one sequence, I am able to predict the 30th indexed data. So that is the logic here. So for that, I am taking empty list for x and y. So that could be seen here. And now this integer I am making use of a for loop here. So this integer I varies in the range window comma length of the data. So window size is already mentioned, say for example 30, and length of the data, which is already seen in the case, that is 1256. The length of the data, what we can see is 1256 samples. So we are covering all the 1256 samples starting from the window size 30. So in that range, what happens to be my x and y? So x is the data, what I am taking here, I minus window is to 1. So, if I say take I equal to 30, this becomes 30 minus 30 is to 30. So, 30 minus 30 is 0, 0 is to 30. So, range of or data of 0 is to 30 means I am going to take 0 to 29 samples because 30 is exclusive. And what is y in my case? It is data of I. So, I is equal to 30. So, let us see it, like how exactly it works. So, if I have to define one sequence, then this is equal to 30 samples because I have taken the window size as 30 samples. So, what my x of 0 comprise is 0th sample, first sample, second sample, so on up to my 29th sample. So, from this I will be getting y of 0. So, for every input, that is for every sequence x of 0, I will be getting this y of 0, the output, which is actually x of 30. So, I am making use of 29 different samples, 0 to 29 samples in order to get this sequence output, which is nothing but my x of 30. So, same thing we can see in the form of a code here. So, yeah, once we have appended the values of x and y, once we have created this x and y, we need to return those in the form of an array of x and array of y. So, I have already told you that window size considered as 30. So, we are creating sequence on the scaled data by making use of the window size is 30 here. Window is argument which is to be used, and window size is already defined, the constant value is already defined. So, this is how we are creating x and y. So, now let us see what is the shape of this x and y that we have created. Nothing but we are trying to convert this time series data into a supervised learning format. So, if we remember what is supervised learning, we need to have a set of input features in order to predict some target variable. So, the target variable is already labeled, but for a set of rows, or we have different rows in the data set for which we have the corresponding output. So, same way for a set of sequence we have the sequence output, or for a set of samples within the sequence we have the output y. So, this is what we are trying to do, conversion of time series data into a supervised learning format. So, now coming to the shape of x and shape of y. So, the number of samples are 1226, window size is 30, and one feature we are considering. So, this is a 3-dimensional data. So, RNN always requires the input in the form of 3 dimensions, number of samples followed by window size and the target variable. And y, the output y includes the number of samples and the target variable, that is y. So, on this x and y, we now create the training and the test data set. So, training and test data set, sometimes we can vary in the ratio 70:30 or 80:20, or sometimes industry standards like 60:40 or 90:10. So, in our case, we have done it as 80:20 portion, 80 to 20. So, 80% of the data will go for training, 20% of the data will come for testing. So, we try to avoid the this random sampling, or we try to avoid this train test split here, because we need to follow the temporal dependency between the data samples. So, if we go for train test split, and there if we do not give this shuffling as false, then what happens is the dependency between the data, or current value depending on the previous value, or current value depending on the future values, that particular dependency will be lost. So, therefore, what we do is, out of 1226 samples, the first 80% of the data will go for training, and the rest 20% of the data will come for testing. So, that is what we try to do. So, length of x, that is 1226 samples, we consider 80%, 80% will go for splitting. So, what is my x train, x test, what is y train and y test? So, x train would be all the data that comes up to split, and x test will be whatever data that follows after the split. So, what is the split now? 1226 into 80%, that would be approximately 980 samples. So, 0 to 979 samples would come for training. Similarly, 980 onwards up to 1226. So split is to, from the split, whatever samples we have. So 1226 minus 980, we get 246. So 246 samples would come for testing. So same thing, the same ratio is mentioned both in case of X train, Y train and X test as well as Y test. So now let us see the training and the test data shape. So X train shape, we have 980 samples. As I mentioned here, we have 980 samples. Window size is once again 30, and we have one feature, that is closing price feature. Similarly, coming to Y train, we have 980 samples and one feature. Now coming to X test, the remaining portion, that is 20% of the total data set. So 246 samples, window size is 30 and one closing price. Similarly, Y test would be 246, 1. So now the 1226 data samples which were present in the data set is converted into training and test split in the ratio of 80 and 20. So 980 samples are going for training and 246 samples are coming for testing. So now let us see how the actual idea of sequence creation, how we have divided this X and Y. So already it is mentioned here, one sequence is equal to 30 samples. So my X of 0, that is the first sequence or the 0th index sequence, comprises of 0, 1, 2, so on up to 29th sample. For this, if I am predicting the output, I will be calling it as Y of 0. So Y of 0 is nothing but X of 30. The 30th, making use of this 30 samples, whatever the 30th index data is there, that becomes my output. So same thing, we'll be able to prove even with the help of the code. So X of 0 comprises of an array with the 30 different samples, 0, 1, 2, so on up to 29. So for this X of 0, I am predicting Y of 0, which is an array of a single value. So that value predicted is for these many samples, for these many values, the next value is 0.11. So same thing, we will be able to even verify. So X of 30 comprising values from 30 to 59 here. So the first value is the 30th value. So this answer or this value is same as this. So one more example we can take, X of 1. So X of 1 is the sample, the number of samples is starting from 1, 2, 3, so on up to 30, it varies. So X of 31 would be the answer, which is nothing but Y of 1. So if I give X of 31, this is the 31st sample. So this is same as this. So we are able to get the output by creating a sequence. We are able to get this output with the help of this particular sequence. So here we have looked into examples, like 1 or 2 examples. So let us see graphically how exactly the representation goes on, or graphically how we'll be able to visualize it. So taking the considering the entire data set, I'm trying to plot the time versus the closing price. So on the x-axis we have the various timestamps, on the y-axis we can see the closing price. So I'm trying to plot a figure. Figure is a function available from matplotlib. So figure, I'm trying to plot a figure of figure size 10,4. So I'll be able to see the x-axis or the width as 10 inches and the height as 4 inches. Therefore 10,4 here. And from the same matplotlib, I am trying to get the plot function. I want a plot of the closing price. So from the data frame that is created, I want only the closing price. Okay. So therefore the closing price. And let the title for this particular graph be Apple stock closing price or time series data. So we will be able to see the title here. On the X label, the X label is time. So this is time here. On the Y label, I want to see the closing price. So this is the label given to the Y axis. And finally, I want to show the figure. That's why I'm making use of the show function from matplotlib. So this is the code for seeing the closing price versus time. So time on the x-axis and closing price on the y-axis. So we can see the various years, and as years pass by, the variation in the closing price. So we are able to see some trend here in the data. Now let us see how exactly one input sequence has been created for 30 different samples or 30 different time steps here. So 0 to, on the x-axis you are able to see the timestamp. So 0 to 29, it comprises of 30 different samples. So that 30 different samples is one input sequence for me. So same thing you are able to see here. So x of 0 is nothing but 0 to 29 samples. So I'm once again trying to plot a figure of figure size 8 inches in width and 4 inches in height. I want to have a plot of only one sequence, that is x of 0. So this graph is for x of 0. I want to have the title as one input sequence 30 time steps. So same thing you're able to see here. And on the x label, let the label be time step, and on the y label, on the y axis, let the label be close price. So once again I want to show this graph. This is how the graph looks like. So we can see that we are able to plot it on a normalized data. This is a normalized data here. Now let us see how from 30 samples we are able to get the 31st sample, or first 30 samples and giving the output for the next sample. So we are able to see the graphical representation of a sliding window visualization. So what exactly is being done in this graph? I take some integer, say 30, let the window size, let the number of samples taken for one sequence, that also be 30. So I'm trying to draw a figure of figure size 12,4, 12 width and 4 inches in height. So I am trying to get the full series present in my data set, as you can see, and I want to see how the sliding window works, nothing but how my input works as well as how my output works here. So I need 3 different representations here. So I am trying to plot the data frame comprising of all the closing price values by using some color. So randomly I have chosen this as a light gray color. So you are able to see this light gray shade for the full time series data. So as I already mentioned, there are 1226 different samples. So 0 to 1225 samples we are able to see with the help of the gray shade. So let the label given to this is full series. Then we have the sliding window concept. So already mentioned, so I minus window size up to I, that will be the range of values for the input sequence. So same thing is mentioned here, 30 minus 30 comma 30. So 30 minus 30 happens to be 0, 0 comma 30. So 0 to 29, 0 to 29 is one input sequence, or the first input sequence in my data set, which should give me the 30th sample. Okay. So those values, I minus window size is to I, let it be represented using blue color, let the line width be 2, and let us call that as the input data or the input window X. So that could be seen here. Okay, input sequence in the form of a blue color. And what is this target y? Target y is nothing but I, the value of I, the value of integer that has been taken here. So I want to have a scatter plot of that I. Scatter plot is nothing but like a dot point or a one data point, what we want on the graph. So let it be a scatter plot. Once again, from the closing price, I want to have all the values of I. So in my case, I is equal to 30 here. Let it be represented using red color. Let the size of that scatter be 100, and let me call that as a target Y. So same thing we are able to observe here. And let the title of the graph be sliding window visualization. Let the X label be called as, this is the title, X label be called as time, and Y label be called as closing price. So let me also show legends for different colors used here. So the legend, this is the legend. It can appear on any portion of the data or any part of the data. So this is left top, same way it could be here or on the center based on how the graph appears. So by default it has chosen this left top portion of the graph. And I want to show this graph. So in the legend I am able to see this full series because we have given the label for full series here. We have given the label for the input data as input window. So input window in blue color, and then the target Y, which is in red color. So the color mentioned is red here. So we have 3 different representation. So once again, summarizing this gray color is the full data set, what we are able to see, that nothing but the closing price present in the data set. So there are 1226 samples varying from 0 to 1 to 25, 1225. Now I am making use of 30 samples in order to define it as one sequence. So 0 to 29 is the input sequence, for which I have to get the output value y, which is the 30th sample, which is the 30th sample. So that is indicated using red. So same ways as Windows slides, every 30 samples it is going to take and predict the 31st samples, or every 30 samples it is going to take and predict the next 31st sample. So likewise it can continue until the full data set. So this is the graphical representation for sliding window visualization. So now when the data set is ready for implementation, it is ready to go into vanilla RNN or different RNN architecture, we will see the implementation of 4 different architectural variants. So as a pre-processing, we have scaled the data, we have created a sequence of data. Now the data is ready to go into model building. So the first variant is vanilla RNN, also called as simple RNN. So here we will have just the RNN, a simple RNN architecture which comprises of the input layers, the hidden layers and the output layers. So let us see how exactly it works and what are the trainable parameters in this simple RNN. So we have the sequential layer because the layers have to be stacked linearly. So model RNN is a variable, okay, and we have the sequential function working on this simple RNN. Let me consider 50 different hidden neurons. Let the return sequences be equal to false. Why we make this return sequence equal to false is because only after 30 samples we need the 31st sample. So we don't need the output after every sample. After the 0th sample or first sample, second sample, we don't need the output after every sample. That's why we make the return sequence equal to false here. We want only at the completion of one sequence we want the output. So this is false in this case. So to the simple RNN, what is the input? It is a window size. In our case, it is 30, 1. So one feature we are giving as an input. So therefore, window size, 1. So this is a 2-dimensional. But earlier I have already mentioned as RNN requires 3-dimensional input shape. So here we need not explicitly define the number of samples, but because it is already defined earlier, we did not define it explicitly because RNN makes use of it. Makes use of that data implicitly. So input data shape is equal to window size, 1, and we need one fully connected output layer, so dense of 1 here. Now I want to perform training or a compilation of the data. So for that I am making use of the optimizer called as ADAM and the loss function called as MSE. So as mentioned earlier, optimizers are required to update the model parameters according to the loss function. So at what value of a model parameter or at what value of a hyperparameter the loss function is very less. So accordingly this optimizer will give us the apt values of the model parameters. So we can use different kinds of optimizers. For simplicity we have used this ADAM optimizer here. And loss function, since this is a regression problem, we are predicting a number here. There are different regression performance metrics like a mean square error, root mean square error, or mean bias error, logarithmic error, absolute error. Any kinds of loss functions could be used here, or multiple loss functions could be used. So for simplicity, I'm just making use of this mean square error because I am good to go ahead with only understanding what is the magnitude or what is the value of this loss function. I'm not interested in the direction of this. So mean square error is the difference between the actual output squaring of this divided by the number of samples present in the data set. So mean square error, number of samples are defined by n here, number of samples are defined by n. So this is the average value what we are getting. So y test is the actual output that we have in the data set. Y prediction is the output that is defined or predicted by the model. So difference between them, and then square it. This will give us the squared error. This is the squared error. So this is the loss function, mean square error function that we are using. And then after training the model, I want to see the summary of the model, like how many trainable parameters are there. So therefore, I want to have a summary of that particular model after running. And then, model RNN, that is a variable in which I have defined my simple RNN function. So I want to fit that on my training data, say X train and Y train. Let the number of epochs be 10. So epochs is the number of times the model goes through the training data. So we want it to be, we want the model to go through the data for 10 number of times. So epochs equal to 10. So always the users are able, free to decide the number of epochs. Sometimes it is based on the number of samples present in the data set also. So we define the number of epochs as 10 here, and the batch size as 32, because let us always have the batch size a little higher than the input size, so that the information from one hidden state can easily go to another hidden state, or from one hidden neuron it can easily pass on to another hidden neuron. So let the batch size be always greater than the input sequence size. And then I have my test data, nothing but the validation data, that is X test and the Y test. So after running this code cell, I have got this output as output shape and the number of parameters. So for the simple RNN that have run with 50 neurons, the output shape is none, 50, and the parameters are 2600. That's because we have the simple RNN parameter calculation formula. So the number of parameters will be equal to number of input features that has been used into the hidden neurons that are used, plus the number of hidden neurons into hidden neurons plus the hidden neurons. So this is basically the weights required to reach from the input layer to the hidden layer. Same way, these are the weights associated with the hidden neurons, and this is the bias that is present in every hidden neuron. So from the input layer, we are trying to reach the hidden layer. So what are the parameters that are necessary for calculation? So in our case, the number of input features are 1, the hidden neurons are 50 plus 50 into 50, because hidden neurons into hidden neurons, plus the bias associated with every hidden neuron. So every neuron has its own bias associated with it. So therefore, it is 50. So when calculated, it is 2600. Same thing when we calculate for the dense layer or for the output layer, the output shape is 1. Here the output shape, in case of simple RNN, we are getting the output of vector size 50 here, because we have 50 hidden neurons. Now coming to dense layer, which is nothing but the output layer, here the vector size is only 1, because we have only one output layer, which is fully connected output layer. But the number of trainable parameters are 51 in this case. That's because when we try to reach from hidden layer to output layer, the calculation is this way. Dense layer formula, input units into output units plus output units. So what are these input units? Those are the inputs coming from the previous layer, that is a hidden layer. So we had hidden layers, 50 neurons. So this becomes 50 into one output layer, that is 1. So 50 into 1 plus the bias associated with the dense layer or the output layer. So that is 1. So 50 into 1 is 50 plus 1, which is equal to 51. So total number of trainable parameters are 2651. So we will have to add up these two values, the trainable parameters in the hidden layer as well as the dense layer. So put together it is 1651. So this is about the model summary, and now coming to the number of epochs and their losses associated with each epochs. So epoch number 1, we are able to see a loss of 0.012, epoch number 2 0.014. We can see the gradual decrease in the loss values, that is a mean square loss. So as the number of epochs increase, except for we are able to see a gradual decrease. So and we are able to see a stable decrease, or we are able to see that stability after epoch number 3. So there is a gradual decrease from 1 to 2, and while coming from 2 to 3 there is a decrease, and then it is stabilizing. So the loss function is stabilizing here. So this is all about a simple RNN. Now having the simple RNN, it is possible to have different variants of RNN. So if we are having it in two directions, simple RNN, forward direction and backward direction, we will be able to get the bidirectional RNN. Suppose we stack simple RNN on top of that one more RNN, then it becomes a stacked or the deep RNN. So the second one what we are going to discuss is the deep or the stacked RNN, followed by bidirectional RNN and then the stateful RNN. So before that, we have the prediction part. So let us do this prediction for one simple RNN. The same thing can be replicated for all different architectural variants of RNN. So how this prediction goes on? So model RNN is a variable in which we have fit this training data, and we have run the simple RNN. So model RNN, we want to predict and have the Y prediction on this test data and save it in a variable called as prediction. Once the prediction has been done, let me get the actual values, because remember that we have pre-processed the data, we have scaled the data so that we get the closing price in the range 0 to 1. So, but after prediction, let us have the actual values, let us have the original values. So, I am applying a inverse transform on the scaled data. So, we have already made use of this min-max scalar. So, I am trying to apply a inverse transform on this predicted data and then store it in a variable, same variable called as prediction. So let's get the actual data on, let's get the actual data also in a inversed way, in the form of a unscaled data. So once again the scalar I am applying on the inverse, I am applying on the Y test so that I get the actual data. Now let me have the predicted and the actual values side by side. For all values, for all integers in the range, length of the prediction. So prediction, I should be having 246 values, because my X test or Y test, the training data, the test data, the number of samples were 246. So I should be able to see 246 different values. So I want to print all my predicted values, all my actual values, only one element. Therefore, we mention it as 0 here, only one element. Let me have two values after the decimal point. That's why we write it as dot 2f here. So we are able to see only two values after the decimal point. So I want to see what model has predicted and what was the actual value. So actual value was 201.03, but the model has predicted it as 202.3. The actual value was 202.24, but the model has predicted it as 203.18. So on, for every actual value we have the predicted value. Nothing but this is Y test and this is Y prediction. Difference between them is the error. So if we are able to map it using different loss functions, then we can go ahead with any kind of loss functions like mean square error, root mean square error, bias, absolute error or logarithmic error, and so on. So graphically, let us explore what is this predicted and the actual values. So I am trying to have a plot of actual and the predicted values. So once again, I am making use of the figure function which is available in matplot library. I am trying to plot the actual value. I am also trying to plot the predicted value. Let the label given for the actual values be actual. Let the label given to the model predicted values be predicted. Let the x label, the label for the x-axis be time step. Let the label given to or the name given to the y-axis be value or nothing but the closing price. So let us have a legend in order to differentiate between the actual and the predicted value. So blue, by default the colors would be blue and orange because I have not explicitly defined what colors I want. So by default it will start with blue, then goes to orange. So we have a separate legend here in order to differentiate between the actual and the predicted values. And then we need to show the particular plot. So we have plot.show here. So we can see the difference between the actual and the predicted values. So it's not like at all points the values are the same. The error is definitely there. That's why we have got different loss values. We can see it here. We have a different loss values, even though they are less, but still we have the MSE values. Coming to the second variant, that is the deep or the stacked RNN. So here stacked means we are having a simple RNN. On top of that, we can have n number of simple RNN structure. So this makes the structure or the architecture a little complex. But what happens is here we'll be able to get the short-term dependency as well as the long-term dependency. Say one of the layer can deal with daily data, how the stock market is varying daily, or stock market closing prices varying daily, and the other layer can deal with monthly data or weekly data, how the value is going to vary weekly or a monthly basis. So different layers or different RNNs can do its own function. That's why we can have multiple RNNs, which gives rise to a structure called as stacked or a deep RNN. Because the complex is little deep, we also call it as a deep RNN. So again, once again, the sequential function, we have the simple RNN with 50 different hidden neurons. Written sequence is equal to true because the information has to pass from one RNN to the other. So we keep this written sequence equal to true, unlike the previous case, unlike the case of simple RNN where we kept it as false, because we didn't want the information we had only one RNN, so we didn't want the information to be going from one RNN to the other. There is no other RNN. And here the input shape is window size comma 1. So window size is once again 30 comma 1. After this simple RNN, we have one more simple RNN with 50 different hidden neurons. Followed by that, we have the output layer. So basically, we have a simple RNN structure which needs the input in the shape of window size comma 1, that is 30 comma 1. Then we have the hidden layer with 50 neurons, followed by another simple RNN with 50 hidden neurons, followed by the output layer, which is a fully connected dense layer or a fully connected output layer. So once again, compilation using or training using the optimizer Adam and the loss function as mean square error. I also want to see the summary of this deep RNN architecture. I also want to have a history of all loss functions or the loss values so that I can plot it later. So therefore, I call it as history underscore D, name given to the variable here. I want to fit it on the X train and the Y train, my training data. Let the number of epochs, batch size and validation data remain the same, because we are trying to compare all these variants at the end. So let us not disturb any of the hyperparameters that we have already considered. So we have the first RNN structure here. The output shape would be none, 30 and 50. Why 30 and 50 is window size is 30 and then we have the 50 hidden units, because the information has to go to the hidden layers. So we have already seen this calculation 2600. We have already seen this calculation. Input features into hidden units plus hidden units into hidden units plus hidden units. So the first two terminologies are meant for the weights that is required from reaching the input layer to the hidden and hidden layers, and finally the bias associated with the hidden layers. So we have got this as 2600. Same way we have another architecture. We have another simple RNN with only the hidden neurons as 50. So accordingly we are making this calculation. Now the input to this is 50. So input to this is 50 now. Earlier case it was one feature, but to this second RNN or the simple RNN 22 what we have, which is the second RNN, what happens is the vector size of 50 units or the output vector of 50 length is acting as input to this. So 50 into 50 plus 50 into 50 plus another 50. So earlier it was 1. In case of a simple RNN, it was just 1 because we had considered only one input feature. But in this case, we get a vector size of 50 from the previous simple RNN. This is acting as an input to the second RNN. This is the second RNN. whereas this is the first RNN. So this will give rise to 5050 different trainable parameters. So when we add this, it becomes 7701 parameters. So, and of course at the dense layer or at the output layers, once again the calculation remains the same. We are getting it as 1 into 50 plus 1. So, number of trainable parameters are 7701, which is addition of these three numbers. So, let us see what is happening at every epoch. So, at the first epoch, the output or the loss is 0.06. At the second epoch, the loss is 0.0023. Likewise, at every epoch, the values are decreasing. So, it is good to see that at every epoch, the loss is declining. So, this is all about the deep or the stacked RNN, wherein we have two or more RNNs stacked one top of another. Now coming to the bidirectional RNN. So, this is once again built from simple RNN but in both the direction. So, here the basic idea is the current value depends on the past values. The current values can also depend on the future values. So, in order to predict the current value, we are making use of both the data. So, the processing happens forward as well as backward. So, forward processing is current value is dependent on the past value. So, by making use of past data, by taking the history of the data, we are able to get the current data. So, that is forward processing of the data. Similarly, we are coming backwards from the future to the current value. From the future to the current, if you are coming, it is the backward processing. So, here every calculation doubles. Say for example, the trainable parameters. Once again, the number of parameter formula or the mathematical representation is the same, but it happens twice, both in the forward as well as the backward direction. So, number of trainable parameters doubles here. So, what is the benefit of having this bidirectional RNN is whenever we have long term dependencies, then in those case even the future values will have some impact on the current values. So, this is why sometimes bidirectional RNN is helpful. So, how this bidirectional RNN is built? Again, we have the sequential layer. We call the bidirectional function. It is no more simple RNN here. We directly have a function called as bidirectional. Bidirectional simple RNN we need to have of 50 neurons. Input shape we can retain the same 30,1 and one output layer, fully connected output layer. Once again training the data, we are making use of optimizer Adam and the same loss function. We want to have the summary of all the output shape and the parameters and the different layers that we have built in the bidirectional RNN. So, and also I want the history in order to have a plot of all the training losses. So, this bidirectional RNN, which is defined earlier, is fit on the training data X train and Y train. Let the number of epochs be 10, let the batch size be 32 and validation data be X test and Y test. So, now coming to the model summary. So, bidirectional RNN, the output shape is none, 100. Why we have this 100 is because we have 50 neurons for forward processing, 50 neurons for backward processing. So, put together it is 100. So, same way 2600 is doubled now. The calculation once again remains the same. So, number of parameters is equal to input features into hidden neurons. So, that is the weight in reaching from the input layer to the hidden layer plus hidden neurons into hidden neurons. So, to reach from one hidden neuron to the other hidden neuron, we need that weight calculation. So, that is hidden units into hidden units plus the bias associated with every hidden unit. So, in our case it is 50. So, 1 into 50 plus 50 into 50 plus 50. So, that is giving rise to 2600, but it is happening in both the directions. So, therefore, it is 5200. Now, the dense layer calculation would remain the same because we have the input features which is now 100. The input features is now 100, 100 into 50 plus 100. So, now coming to the epochs and the various losses. So, we see at epoch 1 loss equal to 0.0458, and at the second epoch it is 0.0012. So once again we are able to see the decrease in the loss. So as a number of epochs, or as we more and more train the data, train the model, the loss is going to decrease. So this is about the bidirectional RNN. Now coming to the last type, that is the stateful RNN. So the importance of the stateful RNN is that it is different from the normal or the simple RNNs that we have discussed earlier, or the three different types of variants that we have discussed earlier. So in case of the normal RNN, what happens is there is no information that is passing between the batches. So there is no hidden state information that is passing between the batches, or we can say that automatically the information has been reset, or automatically the hidden state has been reset. But what if there are long-term dependencies in the data, or what if the input sequence length is greater than the batch size? Then what happens is, from one batch to another batch, the information has to pass on. Say in the simple or the normal RNN that has been taken, we have taken the one sequence length as 30 different samples, or the window size is 30 samples, and the batch size assumed as 32. So in our case, the batch size is greater than the sequence length. So what if in some scenarios, what happens is the sequence length is greater than the batch size? Then what happens? The information from one batch to the other batch. So this is batch 1, suppose this is batch 2, this is batch 3. So the information passing from one batch to the other batch, next batch, would not happen. So in order to manually control this information flow from one batch to the other batch, or from one hidden state to the other state, we make use of a RNN architecture called as the stateful RNN. So in case of normal RNN, we reset the hidden state automatically. I mean, the hidden status reset automatically, but in case of stateful RNN, we manually reset the states. So how this works is, once again we can assume any batch size, say batch size is equal to 30. Once again I need to have the layers one after the other, so making use of sequential function. And now the input size is based on the batch size, window size as well as 1. So here explicitly we have to mention the three-dimensional data. But in case of normal RNN or all the RNN variants that we have taken earlier, number of samples by default is being taken by the RNN. But here we need to define the shape for the input data. So batch size followed by window size, comma 1. So 32, 30 and 1. Simple RNN of 50 different neurons, and stateful is equal to true, because we are making or we are implementing this stateful RNN. And once again dense layer or output layer, which is a fully connected an output layer. Once again we were making use of this optimizer ADAM and loss function as the mean square error, and I want to have a summary of this. So we can see the summary of this. The first simple RNN 32,50. Once again the parameter calculation remains the same, so it is 2600, and at the dense layer we are getting 51 different parameters. The calculation remains the same here. Now let us decide what is the length of the training data. So one condition in case of stateful RNN is that the training data length should be perfectly divisible by the batches that we have taken, or the batch size that we have taken. So that condition only the stateful RNN implementation is possible. So let us see the batch size as 32, which we have already defined. Now what is this new training length that I want? It is the existing training length which is already there, that is 980 minus length of 980 mod batch size. So what happens in this case is, suppose we have 980, which is the training data length. The length of the training data is 980. but 980 should be perfectly divisible by the batch size, which is not happening in our case. So we need to trim off some portion of the training data. So what we are trying to do is taking the actual length of the training data, and we are trying to take a mod of this. So the remainder after taking this, if we are taking the modulus of this, the answer would be 20. So 980 minus this 20, 960. 960 is actually perfectly divisible by 32. So the condition in case of stateful RNN is the training data should be perfectly divisible by the batch size. If not, we will have to cut off some portion in the training data. So that is the exercise what we are doing here. So training data length is equal to the existing length, whatever length of the training data which is already there, minus length of the training data modulus batch. So when we take modulus, we will be getting only the remainder. So the remainder is 20, 980 minus 20, which is 960. So the current length is 960. We are only taking 960 samples for training. So what is my training data? What is my X train and Y train? X train is whatever length or 0 to this 960. So 0 to 959 samples will be taken for training. Same way 0 to 959 samples. So once this is done, I want to print how much data comes in the training data, in the new training data. So x train underscore s dot shape, that is equal to 960 comma 30 comma 1. So window size and the closing price remains the same. Only thing is, so 980 is now converted into 960. So earlier data it was 980, now the new training length is 960 here. So now the model has to run on this particular new training data set. So in order to have a history for all the losses, I am creating one empty list here. So stateful underscore losses, which comprises of all the losses for every epoch that I am running. So for epoch in the range of 10, once again I limit it to 10. I want the epoch information to be printed, okay, plus 1 each time. Every epoch incremental in the epoch should be maintained here. Now history equal to model underscore stateful. So that model is already defined here, model underscore stateful. I have to fit on the new training data, that is x underscore train underscore s, which happens to be the new training data, x train and the y train. Batch size is batch which is already mentioned, which is 32. Epochs equal to 1 and shuffle equal to false here. Why we need to maintain shuffle equal to false is we do not want to shuffle the data randomly, because randomly picking of the data for training and testing means that the dependencies between the data has been lost. So the information, the current value depending on the previous value, or the current values depending on the future value, that particular concept won't be existing if we shuffle the data randomly. And now coming to storing the losses. So all this is required in order to have a history of losses, so that we can have a nice plot later. So stateful underscore losses, we want to append all the losses after every epoch. So I want one element or one loss for every particular epoch that has been run. Now, as I already told you, normal RNN automatically resets the hidden state. But in case of stateful RNN, we have to manually do it. So how do we manually do it? Is for every layer, I make use of the for loop here. For every layer in model underscore stateful dot layers. So every layer in my stateful RNN, okay, or the layers mentioned in my stateful RNN, for all the layers that I consider, I have to check whether I have to reset after every epoch or after every batch is completed, if I have to set my hidden state. So if the function used is has attribute. So then reset the state. So if at every layer we have to reset, we make use of this is function on this every layer. So this is a resetting of the RNN after every epoch. That's why we maintain epoch equal to 1 here. We call epoch equal to 1 because I want to reset the hidden state after every epoch. So even though we mention epochs equal to 10, or in case of normal RNN, once we define epoch equal to 10, once again we don't make use of an argument here within this function. But in case of stateful RNN, after every epoch, since I want to reset, I have to mention this argument epoch equal to 1. So resetting happens at every epoch. So let us see epoch 1, the loss value is 0.053, epoch 2 0.032, then again once again it is decreasing 0.018, so on. Fourth epoch also it is decreasing, but you can see some fluctuation happening in the fifth epoch 0.015, but after that it is getting stable. So only fluctuation we are seeing, or only increase in loss we are seeing in epoch number 5. After that it gradually decreases or stabilizes. So this is all about architectural variance implementation. Finally, let us have a comparison of all the 4 different variants that we have learnt earlier, like the vanilla RNN, deep RNN, bidirectional RNN and the stateful RNN. So once again making use of the figure function and the argument called as figure size of width 10 inches and 5 as height. So I want to have a plot of all the losses or a history of losses that has been stored for simple RNN, history of losses that have stored for deep RNN, history of losses that have stored for the bidirectional RNN, and then the stateful losses. And let the label be vanilla RNN, stack or deep RNN, bidirectional RNN and the stateful RNN. So I want to have a title as RNN architectural variance training losses, which we are able to visualize here. Let the name given for x-axis be epochs. Let the name given for y-axis be loss. And let us have a legend for 4 different architectural variants which can be observed here. Different color variants. Since we have not mentioned the colors here, I already told you blue happens to be the first color, followed by orange, then comes green and then red and so on. Based on how many variants we have, we get different colors because we have not mentioned it explicitly. And then I want to show the figure. So in the figure, we can see that the loss gradually decreases after the first epoch. So let us start with the first variant, that is vanilla RNN, indicated using blue color. So the initial loss is at 0.07 or 0.0, yeah, approximately equal to 0.07 here. Then after the first epoch here, epoch number 1, the value of loss stabilizes. So it has started from a high value, but gradually it decreases or stabilizes. It is a constant value. Coming to the stacked or a deep RNN, we see that it is exhibiting a very high loss, somewhere around 0.035 or 0.04. And after the first epoch, it gradually decreases. And once again, we see that the value remains the same or the model stabilizes. Coming to the bidirectional RNN, it is still showing a very high loss value, that is 0.018, approximately equal to 0.018. And once again after the first epoch, we can see that it is constant. But when coming to stateful RNN, we see that the loss is very minimal compared to the other architectural variants. So the loss value is somewhere near to 0.005. But we can see that it stabilizes only after epoch number 3. So it gradually decreases up to epoch number 3, but from there it stabilizes, it tries to stabilize. But even at epoch 4, it slightly increases or fluctuates, but then gradually decrease. So compared to the 3 different variants, that is vanilla, stacked and bidirectional, stateful RNN has worked a little better when compared to the other ones. So this is all about the implementation of RNN and its architectural variants, namely the vanilla RNN, stacked or the deep RNN, bidirectional RNN and the stateful RNN. So we have done this implementation of the various architectural variants of RNN on a stock market data, that is the Apple stock market data. We have seen how RNN can help us in time series forecasting, which the normal supervised methods or the traditional neural networks fail to do. So traditional neural networks try to assume the data samples to be independent of each other. But in case of a sequential data where they depend on each other, architectures like RNN are of great help. So recurrent neural network extend the traditional neural network by enabling its ability towards sequential data. Thank you.